Welcome to the High Energy Density Science Center Seminar Series. Today I'm pleased to have with us Dr. Riccardo Bonazza. Dr. Bonazza is a professor in the Department of Engineering Physics at the University of Wisconsin-Madison. He received his undergraduate degree in mechanical engineering at the University of Ancona, Italy in 1983 and a PhD in aeronautics at the California Institute of Technology. He has been on the faculty of the University of Madison since 1993. He received an NSF Career Award in 1998, and his research interests are centered upon the experimental study of shock-accelerated flows. Besides the RMI, he has studied extensively the response to shock acceleration of inert and chemically reactive bubbles. So today's talk will be recorded, so if you are not comfortable with that, please sign off. Also, if you have any questions, please enter them in the chat field and I will read them at the end. And otherwise, I am very much looking forward to this talk. And also please be aware that it is unclassified and we also have external people logged in. So be aware of any export controls. And otherwise, please take it away, Professor Bonazza.
Thank you all. I appreciate the invitation to present this work and I appreciate everybody joining in. I believe I know a few of you. Good to have you on board. The material presented today, per usual, is the work of our graduate students. Dan Rees finished a few years ago. He's now at NASA Langley. Chris Noble and Alexander Ames are current graduate students. Jason Oakley is a scientist who has worked with me for many years. David Rothamer, a colleague from mechanical engineering with great laser expertise. So let's dive right in. What we study here is what happens when a planar shockwave shakes an interface between two different gases. We normally talk about different densities, but more generally one ought to talk about different acoustic impedances. That would be a more general statement of the physics we're looking at. And two classes of phenomena are about to take place. The shock itself will be refracted as it strikes the interface, and so there will be a transmitted, a reflected, both distorted in shape. And then the interface will respond in two ways. First of all, it will be set in motion in a rigid translation. But interestingly, vorticity will be baroclinically generated over the interface, and that will cause lead to a total change in shape of the interface and the most interesting phenomena we're studying here. So here's what happens to the shock, reflected shock, transmitted shock, and the interface in motion. And here is this baroclinic vorticity. Baroclinic coming from the misalignment of the density and pressure gradients corresponding to the initial stratification in density and the pressure gradient associated with the shock wave. And because of this vorticity, the amplitude of those perturbations will initially grow in a linear fashion, maintaining the shape. Then it will grow non-linearly, turning into spikes of heavy gas and bubbles of light gas. And then secondary instabilities, mushrooms, Kelvin-Helmholtz roll-ups will occur, all eventually leading to an altogether turbulent mixing layer, which is really what we're interested in studying here. To little more people, all this is pertinent, and this kind of physics occurs in experiment in ICF shell implosions. What happens there, as you know, the shell is probably not perfectly spherical, and the incoming shock is itself not perfectly spherical. And so locally, the physics is exactly the same I described earlier. And so when the shell ablates upon shock arrival, the shock will traverse a perturbed interface thus giving rise to the Rickmeyer-Meshkov instability, leading to the mixing of the shell material and the fuel with possible reduced yield or no ignition altogether. In a very, very simplified theory, the interface is considered purely two-dimensional, single wavelength, infinitely sharp. And we don't have to go into details here. It's important to know that in the early linear stages, the amplitudes grow linearly in time. And one of the governing parameters is this dimensionless density difference, which we call the at-one number. And these other parameters here, k, the wave number, v is essentially the velocity jump associated with the shock, so it's an indirect measurement of the shock strength. Now, much more interesting and much more realistic are initial conditions that are multimode, three-dimensional, diffused, and therefore the linear theory I just glanced over very quickly will go out of use, because linear theory only applies when the amplitudes are significantly smaller than the wavelengths. And so for interfaces with a decent wave number content, high wave number modes saturate very quickly. There is nonlinear mode coupling. And so linear theory goes out the window very, very quickly. Hence the need for calculations, experiments where theory hasn't really written the final answer yet. And this is what I consider a very valuable set of comparisons between experiments in Livermore and experiments in the universities. Temperatures are, of course, orders of magnitude apart. That's by definition because you operate at prototypical conditions, and we deliberately separate the fluid mechanics from everything else. Length scales, ours are much larger than yours. Time scales, the same. Density scales, the same. Yet, when it comes to the Mach number and the at-one number, we operate in reasonably similar regions. And so, as far as the fluids go, our results can be scaled, can be of use, can be compared with the proper HED experiments. And there is that paper by Jason Brandman and his team that pursues precisely this conversation. Many years ago, Bruce Remington visited me, and we did a quick number. This is at least 20 years ago. I had just started the shock tube facility, and at that time, we estimated that one NIF run amounted to about 1.5 years of my support for myself and my students. So I hope I make the case that there's value in marching these things in parallel between the universities and the labs. All right, so what are we after in broad strokes? We definitely would like to add to the understanding of the physics in front of us, and in an era where calculations are important and code development, especially at the lab, occupies such predominant activities, we feel it's useful and beneficial to provide high quality, high resolution data that can be used in part to benchmark those codes. So, how are we going to go about this? In most modern shock tube experiments, most of the people in the community tend to measure entire fields nowadays, so at least velocity and or density. For years, I've been trying to come up with effective ways to measure temperature, it proves very, very difficult, very challenging, more so than density or concentration. From these fields, we can then extract all sorts of data that people have always studied, be it experiments or calculations, macroscopic properties, statistical quantities, spectral studies, for the purpose of understanding these mixing and dissipation processes, and maybe elucidate what the effect of the initial shape, the atom number, the Mach number are on these processes. This is a schematic of our shock tube. Some of you have seen it live. It's unusual by university standards. It's a 9-meter tall tube. The length is not the peculiarity. The peculiarity is this very large cross section here, 25 centimeters square. And the reason for making a tube this large is that, especially upon reshock, the flow will be affected by boundary layers that develop at the walls. So making a large cross section minimizes the effect that these boundary layers have onto the bulk of the flow in the middle of the tube. The tube is structurally quite massive. It can take shock waves up to Mach 5 in atmospheric air, which leads us to, well, pressures that for us are large, for you, they're laughable. But we could, in principle, do this without breaking anything. The problem with very, very high Mach numbers are not so much the pressures as the temperatures, for reasons I'll discuss momentarily. And this is an actual picture of the tube. So this is the driver section. A diaphragm is mounted right there between the red and the black pipes. And when the diaphragm bursts, a shock propagates downwards. And there's a floor here. This is the basement. This is the test section where all the interesting stuff occurs. Now, to prepare our initial condition, start by evacuating the tube completely with a diaphragm in place up high. And we inject a stream of heavy gas, typically argon, from the bottom of the tube, from here, and a stream of helium doped with acetone vapor to act as a fluorophore for laser-induced fluorescence measurements from the top. The two streams meet at a certain location that we can adjust by adjusting those flow rates. And any excess flow is directed to a vacuum pump so that a planar stagnation surface establishes here with the light gas on top of the heavy gas. Then we take the same two gases and we inject them sideways in reverse order this time, with argon on the top and helium doped with acetone on the bottom, right across that stagnation surface. So this is the boring initial part where there is no side injection. This is what the shear layer looks like once we inject sideways. These are PLIF images, so these are concentration fields. Light is pure helium with acetone, and dark is pure argon. And this is the same view with added titanium dioxide particles injected to eventually perform particle image velocimetry and capture the velocity field across the interface. Indeed, to be sure we measure the field well above and below the interface, we add some particles with two separate injections other than the injections that make the shear layer proper. So these are snapshots of those initial conditions. Next, I'll show you a motion picture, and I'll repeat it a couple of times. So black is argon, which is not doped with acetone, and so does not fluoresce. And it's heavy, and so tends to drop. Light is helium, which is doped with acetone, fluoresces a lot. It's light and wants to rise a little bit. The whole field of view is about 25 centimeters, the whole cross-section of the shock tube here. So I would say about 5 centimeters in, we have a well-established shear layer. The motion picture looks very unsteady, and it is, but we've done a very extensive study of the spectra over time, and the amplitude spectra are very, very repeatable in time. So we can take 100 different images, and the amplitude spectrum is very consistent. What is highly variable is the phase spectrum, essentially where the peaks and troughs are. But as far as modal content, that part is quite consistent. And then the experiment proceeds relatively simply. One or two lasers emit beams that are steered, turn into vertical sheets, then cut flow in a vertical cross section. Here I showed them distinct, but the two sheets are typically overlapped, so that we're imaging in a single plane. And we use two different wavelengths, one to perform particle image velocimetry in the visible, one to perform a laser-induced fluorescence, typically in the UV, and we have a variety of lasers. The 266 comes out of the same YAG laser that delivers the 532. So there is convenience in using a single laser, but the energy output is much less. We have excimer lasers that require two separate steering and sheet forming optic sets, but they deliver much, much more energy. So for single shot experiments, these are the ideal choice. We have imaging windows up here where the initial condition is to capture at least one image before the first shock strikes. Then we have two post-shock or re-shock imaging windows below the initial condition to image at different post-shock and post-re-shock time. So conceptually, the system is quite easy. In practice, it's a very finicky thing to run, and success rate hovers around 75%. There are missed runs inevitably. That's part of the business. So some of the experiments I will discuss include a single shot PLIF, single shot particle image velocimetry, and then concurrent single shot velocimetry and concentration. And then one series of high-speed laser-induced fluorescence, so high-speed concentration measurements. This is what we have accomplished so far. And here's a typical, it's called XT diagram. It's essentially a time history of what happens. Let's start from this point, the purple star indicating the initial condition, and let's call this time 0. An incident shock strikes the interface and proceeds following this trajectory here. So proceeds towards the bottom of the shock tube, where it hits the wall and reflects upwards. The interface follows this red trajectory, so it also travels downwards behind the shock. And at some point, a reflected shock will strike this interface. This is what we call the re-shock event. So the white star here will simply indicate the post-shock 3 time, which for all intents and purposes is the initial condition for the re-shock part of the experiment. And then, at least in single shot experiments, we will image the re-shocked interface 4 times, 1, 2, 3, 4. And as you see, upon re-shock, the interface hardly moves initially a little bit and then becomes stationary in space. But you will see that while the centroid of the interface doesn't move much, its appearance will change dramatically. That's essentially the main object of our study. It's interesting that the theory from one-dimensional gas dynamics and the high-speed experiments are very well on top of each other, at least as far as the position of the interface is concerned after reshock. So here is a sample 20,000 frame per second cliff motion picture. Yellow is pure helium. Dark is pure argon. Let's do it again. So if you caught it, you even saw the reshock travel by. The most important part to observe is the fact that the interface has become stationary, but the structures on the interface are growing significantly. Then when the interface moves downwards toward the motion picture, that's the arrival of a rarefaction fan that has reflected off the end wall. That definitely marks the end of the experiment. Our students have participated in the summer schools at Livermore many times. This is motion picture that was generated by Alex Ames, who was there, I think, 2 years ago, using the Miranda code. And it's a very similar experiment as the one in our shock tube. So Mach number 1.8, again, helium argon. I apologize, I don't have a precise color bar, but the scheme is very much the same. So pure helium, pure argon, and mixed region in between. The initial conditions they used were very different from the initial conditions we have in our experiments, but it was a very valuable experience in learning how to run Miranda, how to extract data. So we considered that a very valuable collaboration between us and the labs. So what do we do with these fields now? Many different things. Well, I'll call the mole fraction Xi every time I refer to it. And an over bar will always indicate span-wise average. Remember, we image in a plane, so we have information in the direction of motion, the span-wise direction. We don't have information in the third direction, the one normal to the first two. That is not available with planar imaging. So we can extract the thickness using a weighted integral of the concentration. This thickness is clearly a function of time. We can identify the initial thickness before the shock or before the reshock strikes. And we can identify the centroid of that interface, which is also a function of time. And with these quantities, we can then generate normalized versions. We can either normalize by a constant, like h naught, and sometimes we choose to normalize by a non-constant. So we normalize the displacement or the position within the field of view, offset by the centroid. We normalize it by the instantaneous thickness of the interface. A common way to normalize time is this: time multiplied by the initial growth rate of the thickness divided by the initial thickness. But there will be other versions that I will propose later. It's interesting, Brandon Morgan and others proposed to use this expression here for its log and call it number of generations instead of time. It's a perfectly acceptable substitute since h is a function of time itself. This is a very simple depiction of the standard deviation of the concentration field, which appears to be more narrowly peaked at the early times, right across the interface, right across the centroid, and more spread out at later times. In studying these macroscopic geometrical properties, this is a very often cited law proposed by Michaelian many years ago, that claims the initial growth rate ought to be proportional to the reshock actual number, a velocity jump, and a constant. The constant has been the object of all sorts of calculations, experiments, estimates, and long ago, rocket-based RTI experiments had come up with a constant of 0.28. Calculations had come up for three-dimensional RMI with 0.38. In our estimates, we're talking reshock here, the constant seems to be much higher, 0.57. I would say the final word hasn't been written yet. And here are examples of what these high-speed experiments look like frame by frame. And what I want to point out here is the following. Here are three series, high-speed 1, 2, and 3. The Mach number is essentially the same. We had some difficulties with the actual number because of the acetone seeding system. We have just rebuilt it. It's much, much better now, so we can probably hold this under much tighter control than we had before. But regardless, it's interesting that these are the pre-shock initial conditions. So the interface, excuse me, pre-reshock. So the interface has been shocked, has translated near the end of the wall. It's about to be struck by the reflected shock. The shear layer was the same in all three cases, and yet by the time the reshock is about to strike, the instantaneous initial conditions are very different. So 1 and 3 are somewhat similar, but 2 is pronouncedly different. The consequences are then visible in the time series that follows, this and this being similar to each other, whereas this one being way messier. The middle initial condition apparently having way more wavelength content, wave number content than the other two. And yet, at least at the very early times, the initial growth rate, macroscopic growth rate, seems to be pretty much the same. Later, those initial conditions seem to have an effect and the growth processes diverge. Now, another thing that people have studied, and that is important to understand, is the notion of mixing threshold, isotropy, homogeneity of the layer. And one tool to do this in turbulent studies is the Taylor microscale. It's at least a starting point. So there are a couple of different ways to determine this Taylor microscale. One is the autocorrelation method, which takes the correlation of either component of the velocity. I'm writing here for the transverse component in the x direction, but we could do the same with the streamwise component in the z direction. And then once we have the autocorrelation, we can identify the osculating parabola to that correlation, and from that initial radius, the radius at the zero value of the correlation parameter r, extract the Taylor length scale. Or we can use the statistics of the field in a different way, use the statistics of the field itself and its gradient. Again, can use the x component of the velocity and its x derivative, or the y component and its z derivative. And in either case, we identify the Taylor scale as essentially the mean value of these distributions. When all is said and done, it turns out that the Taylor scale in the streamwise direction, in our case at least, always appears to be less than that in the spanwise direction. And we can average between the two techniques, the autocorrelation and the variance, and we can sum the X and Z versions in quadrature and plot versus another dimensionless time. It doesn't matter what the dimensionalization is, but it's a dimensionless time here. And observe that the lower Mach number, about Mach 1.6, the Taylor scale doesn't quite seem to have plateaued out, whereas it does seem to have plateaued out at the lower Mach number. Granted, it would have been better to have another point in this series, but because the Mach number is larger, the time available to image the interface is less, and so we couldn't, in our experiments, capture a data point out here. According to this, one would conclude that for the larger Mach number, lambda t has saturated, suggesting that the flow has reached isotropy. But we will see shortly that there are other indications that suggest otherwise. Once we have a Taylor lambda scale, a Taylor scale, excuse me, we can calculate Taylor scale Reynolds number, and from canonical turbulence theory, extract a macroscopic Reynolds number. So these are the Taylor Reynolds number here. These are the macroscopic Reynolds number here. Dimotakis in 2000 proposed a value of around 10,000 or so for a threshold in the Reynolds number that marks the onset of full homogeneous turbulent mixing. It would seem, again, that at a late time in the large Mach number case, macroscopic Reynolds number has definitely exceeded that threshold. Yi-Zhu has made some additions to this constraint, and this may not be by itself sufficient to claim full transition to turbulent mixing, but let's say that at least there's some indication that the flow may be there by now. So then there's another way to look at isotropy, which is based on the structure functions. So structure function is essentially an average of a power p of a spatial correlation. Here we must construe h star as marking time. So we have spatial variable, and time. We can calculate the integral over the entire thickness or the entire field of view of these structure functions and study their exponent, the exponent of this integral in log-log representation. Kolmogorov, Obukov, Korsin claim that for homogeneous turbulence, this exponent should go like p over 3. Now, let's take structure function number 2. The color band marks time. Blue is early, 8 is late. First series, second series, third series. So roughly same Mach number, same actual number, just accidentally different initial conditions immediately before reshock. None of these seem to indicate that they have reached a 2/3 exponent as KOC scaling would require, claim that we have homogeneous turbulence yet. Okay, if anything, in here, there may be a change in slope from the early to the late times, maybe a little bit here, much less so in this case. In this case, it seems that that slope stays pretty much fixed. More interesting, if we go here, this is the exponent versus the order of the transfer function. And cases 1 and 3 definitely don't fall onto the predicted slope here, predicted by Crackman, that says that zeta sub p ought to follow this law. But at least they seem to show a tendency from the early time, the blue, towards the late time, the orange, to go towards that slope. The middle initial condition is more interesting because it seems like it's already almost there, already on that line from the very early times, because blue is already here. So this suggests that the initial condition modal content is extremely important when it comes to establishing how early, if at all, we march into a homogeneous regime. Change of subjects. Power spectra and dissipation. Another very common topic in the study of turbulence. So this time I'm going to indicate a Fourier transform with a hat and a complex conjugate with a hat and a cross. So we can extract the Fourier spectrum of our concentration fields, and I can integrate them over the height of my field of view. And plot them versus time. Again, blue is early, orange is late. And observe how these spectra change. One of the first things people always look for is this minus 5/3 region, referred to as the inertial range, typical of well-developed turbulent flows. More interesting to us are these tails here, indicating the dissipative regions of the spectrum. And there is a prediction of minus 17/3, but that's for the case of very, very small Schmidt numbers. Our Schmidt number is about 10%, so it's not that small. And our results, if anything, indicate consistently across all three pre-reshock initial conditions a value of minus 11/3 instead. And lastly, I want to spend a few slides now on one topic that my students somehow has really taken to heart, and it's to zero in on a particular term within a generalized energy transport equation, a term that tells us how energy is transported within the interface across different length scales. So whichever the descriptor of energy is, let's call it E, one can develop a differential equation that says that the time evolution is balanced by production, some kind of scale-to-scale energy transport. Then we'll set aside the energy transport in the inhomogeneous direction, in this case, this streamwise direction, to distinguish from this. And then diffusion, and dissipation. So we want to concentrate our attention on this particular term to see if there's anything interesting that emerges from our data. And I'll present 3 or 4 different varieties of this term here, cooked up from a variety of available data sets. Here I'll start from the simulations. Why? Because in this version, we need a simultaneous knowledge of velocity and concentration time result, which we don't have in our experiments yet. So one can show, I'm not going to go through all the derivation, one can show that that term can be written in terms of these transforms, which eventually becomes the product of these two spectra and the sign of this difference between the phases of those spectra. So this is a mixed spectrum, velocity and concentration, and this is just the concentration spectra here. Once I have this term, I can integrate it with the generalized integral with respect to the wave number and calculate this quantity pi. And then I can do two things with pi. One, I can integrate it over time. And in my case, by time, I'll pick a set of frames from those simulations. And these numbers are chosen so that the first shock has already gone by, and the second shock, or the reshock, has not yet struck. So this is the evolution post-shock. And I can plot this integral, or the contours of this integral, versus position within the field of view and wave number. And so it appears that there is not much exchange of energy at the lower wave numbers, where the near zero value of the color bar here. And there is positive transfer, so transfer from the lower to the higher wave numbers, starting at the middle and going towards the high wave number. In the midst of the interface, if this is the centroid, so I would say mostly on the upper part of the interface. Or I can plot the integral of this quantity pi here with respect to z, so the integral over the entire vertical dimension of the field of view, and plot the contours of this integral versus wave number and time. This again is interesting. This is the arrival of the reshock. So up until here, we're basically in this region here. And as we said, there's maybe some negative transfer from high to low wave numbers very early on, and especially towards the higher wave numbers, but it's very short-lived. Most of the transfer, if it occurs, is in this region here. The arrival of the reshock has the effect of essentially suppressing most of the small scales, and that's the negative values of this integral here that essentially indicate energy transfer from the small wavelengths to the larger ones. And after reshock, that energy transfer seems to have much smaller magnitude than the previous one. So, food for thought. And my student figured, since we have this term here, this sine term, maybe we can cook up an efficiency where we essentially measure how much of all the available energy, that would be this, is actually transferred, how much is lost because of this sine term. And so he plotted the efficiency versus the wave number with time as a parameter. So time doesn't seem to do a whole lot. It seems that the efficiency is higher at the larger wave numbers. And it seems that we never exceed maybe 50%. So the phase spectra, not surprisingly, matter a lot. And what these phase spectra are at any given time depends very strongly on what they were at time zero before the first shock struck. Here's a version of essentially the same concepts. And this time we're going to go back to our experiments. But the only experiments we have where we have both velocity and concentration are single shot experiments. So I'm going to show essentially 4 separate snapshots. I cannot do time intervals, but this is something that was proposed by these authors. And in that case, there was a study in magnetohydrodynamic. And so they were really looking at energy transfer between different quantities, between magnetic and kinetic energy, if I remember correctly. But this is just an idea. It's the idea of taking a field and calculating, combining it with its convection term over 2 different ranges of wave number, k and q, calculating the Fourier transform, and then selecting a portion of this Fourier transform in ranges 2 delta wide across these two wave numbers, K and K here. Okay, and then one can show, or at least they did, that this term relates to that pi sub c term that I was interested in before. So if I have these fields and I can calculate this integral, I can somehow crank out the pi sub c scale to scale energy transfer term. So let's look here. These are 4 post-reshock single shot experiments. The first column shows the portion of the field of view below the interface. The middle column is the interface itself, and the right column is the portion above the interface. So it looks like within the interface, the energy transfer is in the positive direction from lower to larger wavelengths, according to this color bar here. And all the energy transfer is always concentrated on the diagonal between K and Q, so along symmetric wave numbers. Below and above the interface, if anything, there seems to be energy transfer in the reverse direction, negative values here, from the larger to the lower wave numbers. So how does this jive with what I showed you before? It's not clear yet. These are all primordial attempts that we're making at a comprehensive understanding. Yet one more. Let's go back to our structure function, second order. Again, a group from Los Alamos years ago showed that one can go back to our pi sub c term from the structure function like that. So we can do exactly what we did before. Start from the transfer function. And this can be done with our speed PLIF experiments because we don't require, excuse me, this has to be done from simulations because again, I need concentration and velocity. I need both. And again, I can integrate over time and plot, in this case, this is the correlation parameter, a length scale, and the location within the field of view. Again, transfers in the positive direction at the larger correlation parameters. Whereas if I march time along the horizontal axis here, same as before, non-match action before the reshock. The reshock will cause suppression of the small scales, so a transfer of energy towards the large wavelengths, and then not much action afterwards. And lastly, here's another approach. We take our concentration field and we apply a kernel. In this case, we use a Gaussian, but kernel could be pretty much anything one wants. It's a filtering operation of the kind used in LES. And one can show, Perry Johnson did, that our pi sub c term can be related to these quantities via this kind of operation. Again, we need velocity and we need concentration, and so I need to work from the simulations. And this can be shown to be written as this scalar product here with a subscript stress and a grid scale concentration gradient. And so one can come up again with some kind of efficiency, the ratio between the actual product and the product of the two magnitudes. Pictures continue to be pretty much the same, integral over time, pre-reshock, excuse me, most of the action in the middle of the interface at the larger length scales, and suppression milder than before due to the reshock identified by this blue sliver here. In this case, this efficiency looks different from what we had seen before If anything, the process seems to depend a bit more on time and to exceed the 50% mark, at least over the times available in these calculations. So, what did we learn? Well, starting from one of the most classical quantities that has been studied for many, many years, to us, it seems that growth rate, macroscopic growth rate constant, is larger than had been previously reported. We know there must be dependencies at least on the initial phase spectrum, which are hitherto unclarified. The post-shock Reynolds number suggests that the threshold for turbulent mixing has been crossed, but a lot of the other indicators suggest that isotropy and homogeneity have not quite been reached. It does seem consistent across all the varieties I presented that after reshock, most of the scale-to-scale energy transport occurs from the low to the high wave number, so it's a forward cascade of energy. But there are variations, at least in magnitude, depending on how we formulate that term and the overall expression for the energy content of the flow. And where do we want to go from here? As you saw, especially in that last discussion of interscale energy transfer, we need to have spatially and temporally resolved concentration and velocity fields. There's no way out. A single high-speed acquisition won't cut it. So we need to perform simultaneous high-speed laser-induced fluorescence and particle image velocimetry. We do have, thanks to my colleague Dave Rothamer, a laser system that can deliver up to 20,000 pulses per second at decent energy per pulse, nowhere near what an excimer laser can do, but we live with what we have. There are high-speed cameras, and we have several of them that can go up to 16 kiloframes per second. Okay, all this is fine, but it turns out that 1 megapixel doesn't quite cut it to perform particle image velocimetry over the full field of view that we would like to image. So for now, we must make a sacrifice and settle for a reduced field of view for the PIV and still image the full field for PLIF. If any of you has a 4 megapixel high-speed camera laying around that you want to lend us for a year, I will be delighted to accept it. And with that, I thank you very much for your attention.
Thank you very much. If anybody has any questions, please type them in the chat field or let me know that you want to ask Billy. And otherwise, please unmute yourself so we can give our speaker a nice round of applause.
This is Bruce Remington. Hi, Riccardo. How are you doing?
Hi, Bruce. How are you? Good to hear from you.
Just fine. I have a question for you. It looks to me like with the amount of mixing evolution you see, you probably mix fluids down to the atomic scale. And I guess my question is, do you have indications of that? And does it have any significance one way or the other? Or is it just an academic question whether you reach to atomic mix?
So, Bruce, our spatial resolution is, let's call it 250 to 300 microns. So I cannot claim physical evidence from my images. Visually, yes, I would say we may be down to atomic level, but I don't have what it would take to really make the claim. Does that answer?
Could you put chemically reactive materials so that if you mix down to that scale?
So that is one of the ideas for the future. Yes, and that's been on our plate for many years. The time may have come. There are kind of concerns and constraints to do that kind of experiments in a university setting, because even with pretty benign hydrogen oxygen mixing, well, you deal with some stuff that people on campus maybe don't like. But yeah, it's an idea. A simple idea would be to have that chemically reacting compound just in the shear layer, not above and below. That would be too large of a bomb. But if I can have just the layer being chemically reactive, that would definitely be a way to test it. We have done it with bubbles, as Paul said in introduction. I've done reacting bubbles, and that was a very small volume, so that was fairly safe. This would be a little more cumbersome because it's a through flow, but yeah.
Right.
Yeah.
Good.
So there's a question from Thomas Pleva, who says, does the shear layer movie show a single experiment realization?
Say it again. The
Does
movie, the motion picture,
yes.
the motion picture. Yeah, the motion picture was taken, I think that was maybe 30 hertz, if that high, maybe 10 hertz. But it was, yeah. When we prepare the initial condition, the shear layer runs for maybe 10, 15 minutes before we actually send the shock, to make sure that it has really stabilized, that it's properly mixed, it's as statistically steady as we can make it. Was that the question?
Yeah, I think the question is really how repeatable those experiments are to some degree, right?
So as I mentioned earlier, when we study the spectra, so we take the motion picture and we look at maybe 100 images. The amplitude spectra are very consistent. The wavelengths and their amplitudes are very repeatable. It's the phases is where in space those peak troughs really line up. That is the jittery part.
Mm-hmm. Right.
But statistically, they're equivalent, but not.
They're statistically,
the
yes, let's put it this way. They're statistically equivalent, but
right.
they keep
So
moving, say, left and right.
yeah, so shot to shot, it's not repeatable, but statistically you can.
Well, nowhere near what you can do on NIF. Absolutely nowhere near. And we are fully aware of this.
So I have one more question, if I may.
Sure.
So you showed some results regarding estimates of the Taylor scale.
Yes.
Do you have any idea what are the errors associated with those measurements, those estimates?
Yes, I should say, maybe, let me see if I can find it. I should have put them there. I would say right here, maybe, but for something in the 3.5 millimeters, I would say a confidence interval of 0.1, 0.2 millimeters, maybe. So it's a little rough.
Well, it's still, it's a good error compared to the variation between those two curves. So
Yeah, it's
all right. Thank you.
Sure.
Are there any other questions? All right, so let's thank our speaker again. I hope you have a great rest of your Thursday, and thank you for joining us. Thank you for
It is I who thank you again. Sometime it will be great to visit in person and do this live. But for today, thank you.
We'll look forward to it.
Take care.
All right. Take care. Bye-bye, everybody.
Bye-bye.
See you. Nice talk.
Thank you.
Thank you. Thank you, Bruce. Take care.